We are here in the Mpumalanga province of South Africa, and we have received permission to film inside one of the world's largest coal-fired power stations. My goal is to take you on an in-depth educational journey inside the Kusile power plant and show you firsthand how electricity is generated.
Welcome to Kusile Power Station. Kusile is in Ndebele and it's a Swati word meaning the dawn has come. Kusile Power Station, once it's complete, it will be one of the biggest power plants in Africa, producing 4,800 megawatts.
To generate electricity from coal, we need resources. The main one is obviously coal, but we also need water and oil. We're going to start our journey at the water treatment plant at Kusile Power Station.
What you're looking at here is the tank farm at the water treatment plant at Kusile. This is where we store all of the water, processed water and raw water. Well, if you look straight, you will be able to see the big tanks. That is where our raw water comes in. And then from that point, it goes into the water treatment plant itself, where it goes through a ultrafiltration system, where we remove all of the solids. And then from there, it splits into demineralized water and potable water. So the potable water is water that we use every day. We just dose it with chlorine, and that is our drinking water and the water for other domestic uses. And then on the demineralized water side, that is the water that we use for power production.
The coal is used to heat up the water, which is then converted into steam. Steam is used to force the turbine blades to rotate. If we look inside the turbine, there are blades. The steam is used to turn the turbine blades. The blades are connected to a shaft. Since a turbine has a common shaft with the generator rotates and converts the mechanical rotational energy into electrical energy. Thus, water is necessary for the generation of electricity, more specifically, demineralized water.
In these tanks, we have demineralized water. The demin water goes through an entirely different step. It first goes into a cation vessel, because we have a resin system here. So it will go into the cation vessels, where we will remove all of the positively charged ions. And then from there, it will go into our anion vessels, where we remove all of the negatively charged ions. And then finally, it goes into our mixed bed, which is actually a mixture of cation and anion resins. So when it comes out there, you have H2O, and that is what we use in the plant to actually heat up and to ultimately generate electricity.
Why do you need demineralized water?
So basically, demin water is used inside the boiler. That's what we are using to generate steam within the boiler tubes themselves. So the reason it has to be demin is to prevent any scaling or formation of any deposits within the boiler tubing on the inside itself, and to prevent any salt deposits on the turbine blades, which will accelerate corrosion on the turbine side and reduce the life of the boiler and the turbine.
Where does Kusile get the water from?
Okay, so Kusile is actually supplied by the Vol scheme.
Say, for example, the water cannot get pumped here. How many days backup or how many days of water do you have on site?
So on a daily basis, we use about 38,000 cubes of water, and on site we keep storage of 19 days without any supply of water from the valve system, if we're not drawing from the valve system.
Fuel oil is needed in a power station. When coal is burned in the boiler furnace, fuel oil is needed to ignite the coal. The fuel oil is pumped to the oil burners, which are lit using propane gas. The fuel oil is used inside the boiler furnace to ignite the coal powder to create a controlled fireball. A large power station such as Kusile has many floors with oil burners situated in rows. Later in the video, we'll go to the burner level and see the oil burners. Musa, behind us we see a tank. Can you tell us a little bit about that?
Okay, so behind us what we have is a fuel oil tank. So one of the primary inputs to coal or electricity generation is fuel oil. With all our Eskom stations, we use bunker 150 oil. in order to fire the coal, or as an initial process in lighting up the unit. What we have on our left-hand side is our fuel oil offloading station. This is where all our tankers will come in and offload on the different lines. We've got 3 lines, mainly for redundancy. In case one line fails, you've got 2 additional lines that you can pump the fuel oil from. As the tankers come in here, we connect the piping into the tanker to extract the fuel oil, which then gets pumped into the station. So by the way, we've got specifications on the oil that needs to come in. We don't just take any oil. It needs to meet the correct spec of the bunker 150. If not, then we reject that particular tanker. Specific viscosity, the specific cleanliness that we want from there.
How many days can you run for without a delivery of oil?
So we store about 1.2 million cubes per tank. The oil is not continuously used. We only use it on light up or to support a unit in case of any instabilities. So it's not a continuous use item, but from what we have here, we can use for about 30 days without any supply. So from the pump goes and gets stored in our tanks. Each tank stores about 1.2 million cubes of fuel oil. And from those tanks, you then have the pump house, which is what we use to then pump the fuel oil from the tank into the different units through the number of heaters to ensure that you've got the correct viscosity of the bunker 150 oil. This is our fuel oil pump house. From the tanks, we go through the heaters and then we pump the oil into the station. We've got your supply lines and your return lines. So each, you've got 2 supplies and 2 return. You must continuously circulate your oil into the lines to ensure that you don't have any deposits lying there or the oil cooling down on the lines. So you're continuously circulating from the units back into the pump house and back into the units again. And your lines are always charged such that in any case that you need oil supply, the oil is at the right temperature, at the right quality for you to can start oil burners. Behind us is our coal yard. Our coal for Kusile comes in through trucking, which we then have a strategic stockpile, which is meant for instances where you don't have supply of coal. So our strategic stockpile, we store about 1.7 million tons of coal, which should be able to burn us at full load for about 30 days. And then we've got the live feed, which would be the coal that is supplied next to the buffalo feeders. Now the buffalo feeders will then transfer the coal from the stockpiles into the conveyor belts, which will go into the station itself. So you've got a conveyor line which has 2 belts inside for redundancy. It goes inside the unit. Within the unit, you've got coal bunkers which will store at the unit itself. So even in an instance where you have failure on the conveyor belt, you've got bunkers that are able to store and continuously supply within the unit itself. So you've got a line that goes through to unit 1 to 3 and another line that goes through 4 to 6, but you also have an interconnecting line. So in an instance where you've got a failure on one, you are still able to supply through that interconnecting line on the different units. At full load, we burn about 440 tons per hour of coal. What we're monitoring on the coal is basically the coal qualities. So we've got sampling at the mine, and we do a random quality checks at the mines, and we also have our own samplings within the station. So as the coal trucks comes in from different mine suppliers, we do take samples on each of the trucks, which we then analyze the coal qualities. If the coal quality is out of spec, we then notify the mine or compare the results with what the mine has, which we then stop that particular mine if we are unable to improve the quality of coal. But we constantly communicate with the mines in terms of the coal qualities, what we're seeing here and what they're seeing on their side.
Is there any risk of the coal catching alight?
Oh yes, definitely there is. So we are actually wetting the coal on a continuous basis because spontaneous combustion is a real risk.
How does rain impact the operation here?
Eskom has a zero harm policy. So again, we are protected in every way when it comes to the environment. So we do have liners on the coal stockyard, and we also have channels running right around the stockyard. So if there's any runoff, it will go into the channels and it will go into our closed dirty water system.
The coal is transported to the units by the conveyor belts. Before the coal is burned in the furnace, it must be ground into a powder. By pulverizing the coal into a powder, it increases the surface area and improves the combustion efficiency. This powdered coal is often referred to as pulverized coal. To crush the coal, mills are needed. We are now going to see the coal mills and the coal bunkers at Kusile.
Where we are now is at 0 meter level. We started from the coal. The coal comes through the conveyor belts into the different bunkers on the different mills. Up here, this is where the coal will be going to unit 1. The structure here, there are hoppers. Now the hoppers, that's where we are storing coal for each mill. In an instance where you would lose a conveyor belt, you have coal bunkers where each mill will be fed from, even if there's no supply from the coal stockyard. The bunkers will carry enough coal to keep the units going. There's 5 mills which would be representing 5 burner levels. We run with 4 mills for full load with 1 mill on standby. In an instance where you have a failure, you put the standby mill in service and you work on the other mill that has failed. So the coal will then come in onto the bunkers, which is then fed down into the different mills.
We are now going to go inside Unit 1 to see the mill feeders just below the coal bunkers. This is at the 16 meter level.
Okay, so what we have here is mill feeders. Remember I said the coal comes in from the coal stockyard into the mill bunkers. This is at 16 meter level, so above the feeder is your coal bunker where your coal will be stored within the units. These feeders are mainly used to control the amount of coal you're depositing into the mill depending on the load that you want to generate. So for low loads, you run it at minimum speed, which will then put in less coal and when you want more load, you increase the speed on the feeder, which will give you more coal onto the mill. You're looking at 5 of them, each one for each mill. The feeders here, this is at 16 meter level. This feeder goes all the way up to 48 meter level. So the amount of coal that you've got in here, you can run for about 5 days at full load without supply into the unit.
We are on our way back to the ground level.
Now looking at the mills themselves, we've got vertical spindle mills at Kusile Power Station. A mill is basically where we grind or we pulverize the coal. So the coal will come at a certain size, but for it to be bent, it must be at a different size from that. So we will then grind the coal inside the mill into a specific fineness, which can then be transported into the different burners. The transportation from a mill to a burner, that will be using primary air fan. We will show you the PA fans at a later stage, but this level here, this is where our mills are located. So these are the different mills. With us, we've got 5 rows of mills.
So depending on the load is how many mills are working?
Yes. For a full load, you're working with 4 mills. And then if you're reducing load, you have to reduce the mill as well so that you are able to send enough energy for that particular megawatt.
Are these reliable?
Well, they are reliable, but we have a standby in an instance where one fails, because they will fail from time to time, or we will take them into service. There's cycles where at a certain hours we take it into a service. Just like a car, after a number of hours of operation, we take it down, we service it. There's different service intervals. So some service is just for minor, other services is major, where you then take out the whole grinding area and replace with new ones. So what you are seeing up there is a classifier. It's what is used to separate the mill particles. As I said, we want a certain fineness on the coal. If it's bigger than a certain size, it goes back for grinding. If it's small enough, then it goes to the burner. These are our fans. So this one here is our primary air fan, which is what we're using for transporting the coal from the mill into the furnace mainly.
Blow it in.
Blow it in, yes.
Where is the fan?
It's inside. If you're looking at this casing, that's the fan casing. Its primary responsibility is to blow the coal inside the mill into the burner. There's pipes that are going from each mill, or 6 pipes, going to the different burners. So the air blows inside the mill, picks up the light particles, which will go through those pipes to the burners. This is what we refer to the primary air. So it does two functions mainly. One is to transport the coal into the burners. Two is to heat it up to the right temperature. It will come in cold, so inside you will then heat it up to about 90 degrees, so that when it gets inside, you don't use too much energy to ignite it. So you've got a PA fan in front, and then at the back, that's the FD fan, forced draft fan, which is then used to assist in the combustion. You need coal and heat for combustion. So forced draft fan is what you're using for combustion air. Goes through, gets grinded into finer particles, gets blown by the primary air fan inside the boiler. From there, you've got your FD fan that are also bringing in air inside the boiler to assist with the combustion. So what you are seeing here is part of the boiler. The structures that you are seeing from outside, those tall buildings, those are the boilers. So this is the bottom part of it. After burning the coal, the ash will then fall into this scraper conveyor. We're going to take it out to the ash dump. This is a conveyor belt for the coarse ash. From here, it goes out to the ash dump. This is a byproduct. So you've got coal coming in from here, goes to the burner, combusts. All the heat goes up. The ash or the fly ash goes up, and the coarse ash, which is harder, then falls down here and goes into the ash dump.
We are on our way to the oil burner level. The oil burner is a crucial component of the boiler, designed specifically to atomize and spray fuel oil into the combustion chamber. This atomized fuel oil is utilized to initiate the combustion of coal, as well as to control the size of the fireball within the boiler.
All right, this is our burner level, our 16-meter level. This is our first row of burners, row 10. So as I explained, that your coal will be coming from the mill, blown up or through the PF pipes inside here. This is where the ignition happens. So each mill has these rows of burners. From the mill comes inside the burner, that's where the ignition happens of the coal. So when you're looking at the actual structure of the burner, you've got your oil lines, you've got your propane lines. So at the initial stages of starting off a unit, you have propane coming in, followed by your oil, which is the fuel oil, which is ignited by the propane, and thereafter your PF or your coal will then be coming in to ignite. Thereafter, you will be taking out your fuel oil as well as your fuel oil, which at that time your coal will then be self-combusting. There's 5 different levels. This is the first row level. It goes up to 36-meter level. We are currently at 16-meter level at row 10. So Kusile boilers are supercritical boilers. You instantaneously flash into steam. So there's no point where you have that mixture of steam and water. At a certain level, it then flashes over to steam. Other boilers will have drums where you separate the water from the steam before it goes into the superheater. In our instance, we don't have a drum. It flashes over to steam due to it being a supercritical boiler. So those are the PF pipes going into the different mills. As I indicated earlier from the bottom, those are the PF pipes. These ones are coming from going to mill 30. Others up there are going to mill 50. So our boilers are front wall and rear wall fired, meaning you've got burners on the rear and the front wall.
Kusile Power Station has 6 boilers, one for each of the generating units. Pressurized steam is used to turn the turbine blades, which then turns the generator's rotor to create electricity. Thus, the steam is used to convert thermal energy into rotating mechanical energy. To achieve this function, a boiler is needed. The primary function of the boiler is to heat up the demineralized water and turn it into steam, which is then heated up further in a series of superheaters. The interior of the boiler consists of many pipes or tubes which collectively span hundreds of kilometers. The tubes form banks which are called superheaters. Superheaters are composed of coils placed within the hot flue gas path inside the boiler. The pulverized coal is transported to the boiler furnace with forced draft air where it is ignited. The coal is ignited to create a fireball which heats up the boiler tubes. Fuel oil is used to ignite the coal. Because of convection, hot air passes over the tubes and in turn heats up the steam inside these tubes. Since the hot steam is contained inside the tubes, as the steam is heated up even further, it also increases the pressure. This increased pressure is what turns the turbine blades and also increases the efficiency of the whole system. We are now going to the generator floor, which is also commonly referred to as the turbine floor, because the turbine is directly connected on the same shaft as the generator, and this is what turns the generator to create electricity.
So we are now at the turbine floor, or the generator floor. At Kusile we have 3-stage turbines. We've got your HP turbine, which is your high pressure turbine. We've got your IP turbine, which is your intermediate pressure turbine. And we've got your LP turbine, which is your low pressure turbine. So the steam comes from the boiler at 560 degrees to the HP turbine, where it will lose some of the pressure and some of the temperature, and then goes back into the boiler through the hot reheat cycle, where it will be heated up again and comes back into the intermediate pressure. From the intermediate turbine pressure, it goes into the low pressure. Now, the HP, IP and LP are connected through one shaft into the generator. The generator has stators inside, and that is what is used to generate electricity. So the amount of megawatts you would want would depend on a clutch system on the generator, how much it will clutch, which will then give you more excitations on the winding, which will give you more megawatts. So your turbine is always rotating at 3000 RPM, and that speed, that's your generating speed. The amount of megawatts is then determined by the generator and the windings. All units are all in one floor, from unit 1 to unit 6. The only things that are separated is the boilers. Each boiler has its separate houses, but the turbines are all interconnected on one floor. So that's your HP turbine, high pressure turbine, and this is your IP, your intermediate pressure turbine, and that over there is your LP, that's your low pressure turbine.
Why do you need 3?
Depending on the amount of megawatts you are generating. Because at first you come in at a higher pressure, 29 bar, which would be going into the HP, the high pressure turbine. In order to ensure that you are able to maximize or your efficiency, you then take the same steam, because it's still hot, you take it back to the boiler, you heat it up back to superheat temperatures, and it comes back to the IP. After the IP, the pressure and temperature will be lower. It's not sufficient to can go back, but in order to increase your efficiency, you use the same steam to drive the shaft by sending it to the LP. So the LP is able to take less temperatures, less pressures, so the steam is not as superheated as you'd get on the HP. But in order to ensure that we maximize the efficiency, we then reuse the steam up until a point where it can no longer be used. It comes here first from the boiler. So after you've put in coal inside, we've got the water, the dimming water goes inside the tubes. That's what gets heated up for us to generate steam. After the number of steam cycles that you would have gone through, it then comes to the HP turbine. The HP turbine is the first turbine which will go through. The steam after the HP turbine goes back into the boiler, which it gets further heated up through the reheat cycle, where we're reheating it and brings it back to the intermediate pressure. So the HP will have 29 bar. IP will then be at a lower pressure, 6 bar, and then you'll go into the LP. So as I said, they are all interconnected on one shaft. So you drive the HP, it drives the IP. The same shaft is connected here, connected there, connected to the generator.
How do you control the flow?
So the flow is controlled through governor valves. On the side here, these are valves that would control the amount of steam that would be going into the HP. This is one of the governor valves or the steam control valves.
It's 4 o'clock in the afternoon now. What's happening here?
So at peak time, we then have to run it at full capacity, meaning we go to full megawatts. With us here, we're generating 800 megawatts, meaning during the day, we'd probably be sitting at about 600 megawatts. And then at peak, we go up to 800 megawatts. That means 100% steam flow goes through the turbine into the different turbine cycles. That is how we are managing to generate full capacity.
So inside here, there's blades and fins.
Yes. So the turbine is made up of a number of blades. So basically, this is a massive fan, if I can put it like that, with a number of blades in it. So the steam goes through those blades. That's how it rotates. So the blades are positioned such that as the steam goes through, it propels the turbine.
A generator consists of a rotor and a stator. The stator is the stationary part of the generator. It remains fixed in place and does not rotate. Its primary purpose is to create a magnetic field. Here is an example of a rotor which is being removed from its generator enclosure. Note how the rotor comes out from the center of the generator. The rotor is the moving or rotating part of the generator. The rotor is attached to a mechanical prime mover, the shaft which is coupled to the turbine. The turbine drives the generator. More specifically, the turbine shaft rotates the rotor because this rotor is fused to the same shaft. The rotor's rotation induces a changing magnetic field in the stator, leading to the generation of electrical currents. The induced current is generated in the stator winding of the generator. These stator windings are ultimately connected to the electrical grid. To give you an example of the size of a rotor for a large generator, here is a rotor which was decoupled from the turbine shaft and removed from the generator housing. This rotor is being lifted onto a platform for repairs. In South Africa, the frequency of the electricity is 50 Hz. This means that there are 50 complete sine waves per second. The rotor must rotate at 3000 RPM or revolutions per minute to produce this 50 Hz output. 3000 RPM is the same as 50 rotations per second because 3000 divided by 60 is 50, which is why the electricity in South Africa has a frequency of 50 Hz. Taking into consideration the sheer size of the generator and the speed at which the rotor rotates, one may appreciate that keeping this machine cool is a highly technical task. Huge currents in the order of over 20,000 amps flow in the stator windings. We are now going to learn about the generator's cooling system.
Welcome to Kusile Power Station. We are standing right in front of a generator. It's a 900 megawatt machine. Let me take you through, guys, the components which are forming a vital part of the machine. On the right hand side, that little drum, whitish in color, it's a hydrogen cooler. There's two of them, one on this side, one on the northern side I'll show you just now. But basically the cooler is supposed to cool what is called an H2 for our generator. So the moving part of the generator, which is the rotor, is cooled via hydrogen. So the hydrogen, we need to cool it down also. We do it via those, it's basically a heat exchanger. Let me take you through to the exciter of the machine. On this side of the generator, we've got what is called the brush gear compartment. So basically at the bottom of the generator, I'll show you later, we've got the exciter. All the power gets transferred from there all the way into the exciter compartment. In here, we have got the the brushes. So how we transfer power from our rectifying unit, we transfer it to the rotor using our brushes. So in there's quite a number of brushes that we maintain each and every week to check if the length is still enough, and then we are able to make sure our machine is nice and healthy. Our generator has got two most important components. We've spoken about the first one, which is the rotor. The second one is the stator. So the stator is the stationary part, so it also needs cooling. So on top of the housing, that little drum on top is the storage for our water. We use water to cool down the stator. So this is what is called the stator water head tank. We store our water there. Down there we've got pumps that are used to pump the stator water up into the generator for the cooling. The hydrogen gas that I've spoken about is highly explosive. It's odorless, cannot be seen via naked eye. But the most important part is it's a highly explosive gas that is used to cool down the rotor, as I've mentioned earlier. Now we need to be able to contain and control this specific hydrogen gas such that it doesn't mix with the atmosphere and create an explosive environment. So we've got a system on the both 9 drive end and the drive end side of the generator, which is called the seal oil system. We use oil to prevent or to seal the hydrogen from escaping outside into the atmosphere. I'll show you the system, how it works down there. We are looking at the hydrogen skid. Currently we are using bottles, so it's like a plug and play type of setup that we've got with the bottles being supplied by external party. But in the future, we're going to have a dedicated plant that is there to produce H2 or hydrogen gas for our generators. So in this kit here, we ensure that our hydrogen is pure, because we don't want the hydrogen to have even a minor concentration of oxygen, because then it makes an explosive mix. So we condition the hydrogen before we send it up at the right pressure into the generator, one for every generator. Like I've mentioned earlier, guys, our hydrogen, we don't want it to escape out of the generator. We also don't want air to enter our generator, because then that creates an explosive mixture. So now the system that we use to prevent or to seal our generator is located down here. It's what is called the seal oil system. So basically we are using oil, pressurized oil, that we send up into the bearings or into the manifolds where the generator is, and then we ensure that the hydrogen doesn't escape and there's no water that comes through. Here at Kusile, we use what is called a 3-circuit sealing system. Most of the generators, they'll use only 1 circuit, where they use oil to seal the system. So we are using a highly specialized system, which is using 3 different circuits to ensure that we have more efficient or more effective sealing. The last important section of the generator is the stator water pumps located on my right hand side. I've mentioned earlier that the stationary part of the generator is cooled using water. So down here we've got 2 pumps that are meant to supply water into the stator and then circulate the water throughout. 2 pumps, 1 pump is always running, next pump is always on standby in the case of emergencies. Okay guys, we are standing in front of the excitation room. Like I've mentioned earlier, for us to excite our rotor, we need to be able to convert our readily available AC power into DC. This is where we convert our AC into DC power, and then we send it to the rotor into the brushes.
The generator converts mechanical energy into electrical energy. On these large generators, huge currents are flowing in the stator windings. This is the current that feeds the power grid of South Africa. This output current, as well as the voltage, needs to be measured to ascertain how much energy is feeding into the grid. The current and voltage also need to be measured for protection of the generator and the grid in the case of faults. In a small AC circuit, we can turn the circuit on or off by simply flicking a switch. We can measure the current flowing in the circuit by placing an ammeter in series with the supply. We can also directly measure the voltage by placing a voltmeter across the load. However, when the currents and voltages increase, direct measurement becomes technically difficult and dangerous. The voltage at the output of the generator is 22,000 volts with a current of over 20,000 amps. These high values pose a challenge to measuring the voltage and current. Devices such as current transformers and voltage transformers are needed to measure these high currents and voltages at the power station. To connect the generator's stator windings to the grid, a circuit breaker is used. This device is far more than a switch. It is specifically designed to handle fault conditions and thus can open the circuit even if there is a current far larger than the normal load current, and it can do this very quickly. For the circuit breaker to function, current and voltage need to be measured. Designing a protection system to maintain the longevity of the generator is complex. Here is a non-exhaustive list of just some of the possible faults that may occur at the generator, as well as a list of topics that are required for generator protection. Rows and rows of protection relays and various instruments are necessary to constantly measure a variety of events to protect this generator. Since the generated current is very high, very thick conductors called busbars are needed to connect the stator windings of the generator to the step-up transformer. An example of a copper busbar is shown, but this image is only for explanation purposes, as the pictured busbar is only rated at 6,000 amps, while the generator busbar is rated well over 25,000 amps and is much larger in size. We were unable to see the actual busbars as they are enclosed in ducts. Current travels in the busbars from the generator to the step-up transformer and then to the grid. We will now see this firsthand.
Up there at 9 meters level, there's a generator and then 6 output bushings going down. 3 of them are forming a start point. Other 3 of them, those ones are taking output current all the way to the grid via the gen circuit breaker that we're using to synchronize, and it also uses to separate from the grid. And then it goes via the gen circuit breaker that steps up voltage from 22 kilovolts all the way to 400 kilovolts to the grid. Right behind me is a CT ventilation system. What we use it is to cool the current transformers at the bus bars, the drop-in bus bars via those bushings. So those CTs, we use them for protection, generator protection, as well as for metering. So this one is pumping air all the way up. As you can see, those ducts going up all the way to the compartment where they are cooling the CTs.
The bus bars coming from the stator winding of the generator travel inside these ducts.
Behind me is an earthing transformer, and up there in those ducts, that's where the electricity is flowing all the way to the grid via the generator circuit breaker and then the step-up transformers to the grid. So all the bus bars, 22 kilovolts bus bars that are inside these ducts, we have put them in an enclosed, isolated area that is pressurized. So these enclosures, we call them IPPs, isolated phase bus bars. So we're keeping them under pressure to prevent dust from going inside. Should there be a leak in these ducts, pressure will blow off the dust to prevent dust from getting inside to cause tracking leading to flashovers in those bus bars. Up there is a generator circuit breaker. It's rated at 22 kilovolts and 25,000 amps. So we're using it to isolate the generator from the grid. So should we happen to have a fault, whether on the turbine side or in the boiler side, this is a generator circuit breaker via the protection system that closes. So whenever we want to resynchronize our generator to the grid, to transport electricity to the grid, this is a generator circuit breaker that we are closing so that we can be synchronized and then we transport power to the grid. This generator circuit breaker, whenever it operates, it's very, very loud. You can literally hear it banging while you are passing by. Okay, these are the 3 bus bars that came through the generator circuit breaker that are rated at 22 kilovolts. And the current running at full load there is approximately 24.9 kiloamps that is flowing all the way to the transformers. And then because of the high current and we want to be able to transport electricity to the grid, we need to step it up at the higher voltage so that the current will decrease so it can be transported properly to decrease also the losses.
Since power stations are usually situated far from the cities, the power needs to be transmitted to the customers over long distances. Good conductors do have a low resistance, but when we need to use very long conductors, such as transmission lines, there is still a resistance in the wire, as well as inductance and capacitance. Using a simplified example that only looks at the resistance, if a power line that is 100 kilometers long has a resistance of only 3 ohms per phase for the entire 100 kilometers, even the small resistance would result in a huge loss when the current is high. Hypothetically speaking, if 20,000 amps were expected to flow in this 100 kilometer conductor, the losses per phase would be 1.2 gigawatts, which is more than the total power produced by Kusile's 800 megawatt generator, so that definitely would not work. Not to mention that the transmission line would have to be huge, which would also be impossible to set up. Thus, large currents cannot be transmitted over long distances as the losses are far too great and the infrastructure is unavailable for this. If, however, the current could be reduced to say 1000 amps, then the resistive losses would be reduced to 3 megawatts per phase, which is substantially lower than the 1.2 gigawatts. Now, a lot more is involved in determining the losses of a transmission line, including inductance and capacitance along the line, but the simplistic example is just meant to demonstrate the main reason for why we have to reduce the current when transmitting the power over long distances. To achieve this goal of lowering the current prior to transmitting the electricity, a transformer is used to transform the current from a high value to a low value so that the transmission losses are greatly reduced. The voltage at the generator output is 22,000 volts, which is fed into the primary side of the step-up transformer. But the voltage on the secondary side or output of this transformer is now stepped up to 400,000 volts or 400 kV. This is the voltage that is fed to the grid. Transformers have a turns ratio. This ratio is the transformation ratio. For example, the voltage went from 22,000 to 400,000, which represents a turns ratio in the transformer of 22 over 400, which is 0.055. Since this is a ratio, it can also be said in the reverse. 400,000 divided by 22,000 is equal to 18.18. Which means that for every 1 volt on the primary side of the transformer, there will be 18.18 volts on the secondary side. This ratio is important as the same applies to the current, however the current is the inverse of the voltage. If the current at the generator was 20,000 amps, then by using the turns ratio of the transformer we can calculate the output current, which is now going to be 1100 amps. This means that the current would reduce by a factor of 18.18. The current coming out of the transformer is now reduced to 1100 amps. This is the purpose of a transformer. It does not change the power though, it changes the amount of current at the output while increasing the voltage, which means that the power stays the same. And by doing this, it allows us to drastically reduce the losses in the transmission lines. This is not without other challenges because dealing with 400,000 volts poses a new set of challenges. But nevertheless, this is the method that we need to use.
Behind me is a generator step-up transformer. So what it does, it step up voltage from the generator of 22 kilovolts all the way to 400 kilovolts. It's rated at 910 mega VA. It's an oil transformer with oil that is cooled by 9 banks, each bank containing 3 fans each. So those fans are running to force cool the oil and is pumped via the fans all the way into the transformer where oil is circulating inside the transformer. Once the voltage has been stepped up from 22 kilovolt to 400, from those long bushings that you see up there, they are transferring voltage of 400 kilovolt all the way to the grid. 400 kilovolt is then transferred to the grid through the SVR and then to the whole grid of South Africa. Okay, behind me is an SVR that belongs to transmission, and then from transmission it's when it can be distributed to the factories and houses and all over the cities, all over South Africa.
The generated electricity travels from the step-up transformer to the high voltage yard via the high tension overhead cables. The higher the voltage, the more dangerous this becomes. High voltage is audible. The 400,000 volts that is fed into the grid is technically classified as extra high voltage, and if you listen carefully you can hear the buzzing sound of the voltage. The high tension cables then feed into the high voltage yard, but we need to keep in mind that everything we saw from the boiler to the step-up transformer is only for one unit. This means that everything is duplicated 6 times. There are 6 boilers and 6 generators at Kusile. Hence, this is why the power station has this appearance. When we walked along the generator floor, we saw 6 generators. Each generator has its own feed into the high voltage yard. The output of each generator is thus connected to its own step-up transformer. Kusile has 12 step-up transformers, 2 for each generator, one online and one as a standby. After the step-up transformer, the high tension cables are then fed into the high voltage yard. Again, this takes place 6-fold. The high voltage yard includes various protective devices such as current transformers, voltage transformers, disconnectors and surge arresters used to safeguard the equipment and maintain grid stability. Control systems are used to manage the voltage, monitor equipment health and respond to faults and disturbances. The high voltage yard thus also has a circuit breaker to disconnect the generator from the grid. One should keep in mind that in order to disconnect the power plant from the grid, an adverse situation must have occurred, and thus the control room engineers need to constantly monitor the voltage, current, frequency, harmonics and many other values, and thus extensive protection equipment is needed throughout the power plant, some of which is found in the high voltage yard. From the high voltage yard, the power is transmitted on transmission lines and distributed to different places in South Africa. Power is now available to the grid of South Africa. Each generator is designed to provide a continuous power output of 800 megawatts. Thus, for 6 units, the planned capacity will be 4,800 megawatts.
Now what you're seeing up there at Kusile, we're using a dry cooling system. Other stations will use a wet cooling system where you'll see a massive cooling tower. In our case, this is what we refer to our cooling tower. It's a dry cooling system. We use fans to cool. This is a much more efficient and environmentally friendly system because you don't lose any water. So everything is a closed cycle. The fans will be used to cool the water, which will condense, and you go back to the water treatment plant for polishing, and we return it back to the boiler. Those big pipes, that's steam. That's steam going up to the fans for condensation. So you've got steam flowing through the pipes. From there it condenses, goes back down. You'd see the blue pipes underneath. It goes back to the polishing plant.
This is what it sounds like to stand underneath the dry cooling system. A coal-fired power station needs a cooling system to cool the steam that leaves the final stage of the turbine. The reason for this is that steam turbines are typically designed to extract energy from high-pressure, high-temperature steam. After the steam has passed through the turbine, it has given up a significant portion of its thermal energy. To recover that energy from the steam needs to be condensed back into water, because the conversion of water into steam is when heat and pressure are generated. Thus, by converting the steam back into water, the cycle can restart. This process allows for the efficient use of demineralized water, which is crucial because demineralizing water is an expensive and resource-intensive process. Another 2 reasons why the spent steam is condensed back into water is that it would take too much energy to recompress the spent steam before returning it to the boiler. It is also easier to pump a liquid than a vapor. The spent steam or used steam flows into the radiator and gets cooled by the many fans that blow over the pipes, which results in steam condensing back into water. This condensed water can be returned to the boiler to be reheated and turned back into steam, completing the cycle. Steam turbines are also sensitive to the quality of the steam. Dry, high-quality steam is preferred to prevent damage to the turbine blades. The condensation process helps improve steam quality. Kusile Power Station uses a dry cooling system which relies on forced air cooling. A wet cooling system uses water as part of the cooling process. A significant amount of water is needed, and a lot of this is lost to evaporation. We can see the white plumes leaving the cooling towers. People often mistakenly think this white cloud is pollution, but actually it's warm, moist air and condensing water vapor. The flue gas is what has the pollutants, and this is the white plume leaving the chimney, shown by the orange circle and arrow. Kusile does not have cooling towers as it uses forced air cooling, which is why there are many fans embedded in the cooling system structure. A dry cooling system uses approximately 60% less water than the conventional wet cooling system, but a dry cooling system is more elaborate and expensive to build. After seeing all the machines that are needed to run a power station, such as the cooling system fans, the forced draft air fans, the mills, protection equipment, lighting and computers, you might be wondering just how does the power plant's machines and domestic appliances get electricity? There is a transformer that is fed just after the generator before the step-up transformer. This is called a unit transformer. Thus, electricity is tapped off from the output of the generator. Those are the bus bars traveling in the ducts. Kusile has 2 unit transformers after the generator. One of the unit transformers is for backup. In the picture, it is demonstrated how the unit transformer taps directly off the main bus bar, but just keep in mind that 3-phase electricity is produced at the power station, so there are 3 bus bars en route to the step-up transformer. Just before the step-up transformer, you'll find the unit transformer. So the unit transformer is tapped off from the main bus bar, which was traveling from the generator stator winding en route to the step-up transformer.
On my left are the unit transformers. These transformers are used to step down 22 kilovolts all the way to 15 kilovolts. So 15 kilovolts is fed to the boards that are supplying our 15 kilovolts loads, like our biggest motors, which are the boiler feed pump motors, FD fans and IT fans, those bigger, higher loads, the forced draft fans that are feeding from the 15 kilovolts. And then from there is where they step down from 15 to 6.6 kilovolts, and then that's where they are feeding all the other loads that are used by the units.
There is another way that a power station can get electricity. Since South African power stations are connected in a grid, the power station can also be fed directly from the grid. For example, if all generating units of the power station happen to be offline, a very unlikely situation, the power station would no longer be generating any electricity. Then the unit transformer would not be able to get any power from the generator. However, if the high voltage circuit breaker in the high voltage yard is closed, meaning that the power station is still connected to the grid via that high voltage circuit breaker, then the grid being still online can feed current backwards from the grid to the step-up transformer, which now would be a step-down transformer as current is going in the opposite direction, thus stepping down the high grid voltage, which in this case would be about 400,000 volts, but after the transformer it would step down to 22,000 volts. So a transformer can work in reverse. So the grid can feed the unit transformer of a power station so that the power station can remain online, albeit now as a load on the grid rather than as a generating station. Since Kusile is still under construction, this situation has taken place during the construction phase of a power station.
Once you burn the coal, what are the byproducts?
There's 2 byproducts mainly. One is fly ash, which then goes through fly ash cleaning system, and the other one is coarse ash. The coarse ash is then transported into the ash yard. Even the fly ash gets carried through the conveyor belt into the ash storage yard, or the ash dam. Yeah. So this is the byproduct that we'll be getting from the coal. You'll recall that the coal inherently has ash, so we have a specification on our coal on how much ash product we can allow as part of the coal specifications that we send out to the industry for the supply.
If it rains, what happens to that ash? Does it get into the groundwater?
I think this is a part where people start freaking out, because if they look at the video, it looks as if all of the ash is simply dumped onto the grass and we leave it there. but it's not the case at all. So the ash dump is designed with a liner that keeps seepage going into the groundwater. And then we also have a dust suppression system to keep it flying into the air. And now obviously when it rains you think, oh, there's so much runoff from the sides. But to prevent that going into the environment, there are trenches around the ash dump also that takes the water to a specific storage area. And that water is again used in the system.
When the coal is burned in the boiler, it releases pollutants, including nitrogen oxides, particulate matter, carbon dioxide, sulfur dioxide, and methane. At Kusile Power Station, a wet flue gas desulfurization system is used to reduce the sulfur dioxide from the flue gas. This is the first of its kind in Africa. The central component of the FGD system is the spray tower or absorber. Within this tower, a reagent, typically a slurry of lime or limestone in water, is sprayed into the flue gas stream. The reagent reacts with the sulfur dioxide in the flue gas, forming calcium sulfite or calcium sulfate, which are solid byproducts. For the FGD system to function effectively, Kusile must maintain stockpiles of limestone. The limestone is then crushed to create the slurry. This process is labor intensive. One of the byproducts of the FGD process is commercial grade gypsum. Gypsum finds a wide range of applications, including its use in construction material for drywall, plaster, and cement. FGD systems are highly effective in reducing the emissions of sulfur dioxide, making them crucial for minimizing harmful pollutants in the environment. Nonetheless, the wet desulfurization method used at Kusile has faced challenges, including a failure in Unit 1. Later in the video, the power station manager will elaborate on some of these challenges regarding the FGD system. In South Africa, sites of national strategic importance, including military bases and power stations, are designated as national key points under the National Key Points Act of 1980. Filming within these key points requires special permission due to security concerns and possible sabotage. To comply with Eskom's requirements, the footage of the control room has been blurred, and this section of the video has been reduced for this reason. The power plant needs to have a control room. This is the central facility where trained operators and engineers monitor, control, and manage the operation of the power plant. It serves as a nerve center of the power plant, providing real-time oversight of all critical systems and processes.
So we just walked into the control room here at Kusile. So on the screens, you will see a plant overview. There will always be a plant overview at the very top. And the other screen is used for the most important trends that we are looking at and are more likely to show the trip parameters. And at the bottom, if you look at those 2, 4, 6, 8, 10, 12 screens, those are just screens as the controllers are operating, so there will be alarms during the operation of the unit, and then they will go to the screen, go and check what's wrong. And each alarm also has a different priority, so they will respond to it differently.
Are there controllers working here 24 hours a day?
Yes, we have controllers working here 24/7, and we usually have 1 to 2 controllers per unit, depending on what's happening. Obviously, during a light up, they can increase the controllers sometimes, just to make sure we are looking at everything and we bring the unit up there safely.
Is this a very stressful position?
It's a very stressful job to be a unit controller, and all eyes are on you. I mean, if something starts to go wrong, you see, will they be able to catch that unit or not? And that is exciting, especially when you see it going down and they manage to catch it before it does.
Okay, so this is Unit 3 control room, and it's manned 24 hours a day. It's quite extensive and a tedious operation with a lot of responsibilities. Seeing that we utilize some of the world's best technologies that's on the market there today. The duties consist out of basically keeping a boiler and a turbine as a unit on load. So to give you the gravity of the situation, the fires that's currently that generates the steam in essence is about 15 meters by 15 meters by 50 meters in size. Your fireball is that big. So you can appreciate the fact that you are controlling this massive amount of energies via a PlayStation. So it's quite a tedious operation with a lot of responsibilities.
So this is the EOD. This is where they look at the grid. They communicate with national control. In an instance where we want to synchronize the unit, they would look at the frequency and then give us permission to synchronize the unit. They are more in control with the national control and communicating with them continuously. So they are looking at all units, all 6 units, looking at the frequency amongst all units in line with what the grid is requiring.
If we want to do a test and we need to lower the load to do the test, we first need permission from national control to lower the load.
Eskom's power stations feed the grid of South Africa. Therefore, there needs to be central coordination to manage the whole grid. Eskom's National Control Centre is the nerve centre for managing South Africa's grid. Managing a power station is a position of significant responsibility and requires a diverse skill set. We will now meet the manager of Kusile.
My position at Eskom, I'm the power station general manager for Kusile.
What is unique about Kusile Power Station?
One, Kusile Power Station is a supercritical boiler. So all the boilers before Kusile was built, they were critical boilers. This one is supercritical, which makes us being able to generate such high megawatts. The second unique feature of Kusile, we are using low NOx burners, which is the technology that we use on our boilers. We are also fitted with flue gas desulfurization plant. It is one of the kind in Africa. It is only found at Kusile Power Station. The purpose of that plant really is to lower our emissions, SO2 emissions, so that we can emit less. So currently Kusile is the only power station that is able to emit less sulfur dioxide emissions to the atmosphere. Also, as Kusile Power Station, we are fitted with a PJFFP, which is pulsing jet fabric filter plant, which is also used to remove more particulates from the flue gas system.
What are some of the technical challenges you experience at Kusile?
One of the major challenges we are facing, as I highlighted earlier, that FGD is the first of its kind. So we are having performance challenges, and we also have got less skill in that area where the performance of the FGD is not at the desired level. We are still building skill so that we can be able to perform better in that area. We are also looking into partnering with various original equipment manufacturers so that we can be able to make sure that this plant's performance is of the high standard. Other challenge that we've got is that, as you may be aware, that Kusile is still a new built power station. It is not completely constructed. So unit number 5 and unit number 6 are still undergoing construction. So currently we have to balance construction requirements and operational requirements, which can be challenging sometimes in a power plant, but we are managing with our colleagues responsible for construction of the asset. Also, at Kusile Power Station is a fairly young plant, and majority of our teams have been with the power station from the beginning. If you study the equipment reliability, you will understand that at the early age of an asset, in a bathtub curve, you will have that infant mortality and failures that are unpredictable. So we are still going through those tedious process, but we believe that with the team that we have, we can be able to understand the failures better and be able to optimize and get reliability better. So that is still work in progress, and we are taking lessons learned unit by unit and trying to improve.
If a generating unit trips unexpectedly, what does that mean for you?
One, when it trips, it means We need to quickly find a way to understand what's the cause of the trip so that we can be able to restore it back because the impact of it on the grid is huge. Secondly, as a power station general manager, then I have to get continuous feedback from my teams around the investigation and whether we are able to return the unit safely or not. So when a unit typically trips, it then disturbs because you then need to put all the effort and support the guys to be able to return it. When the unit trips, we have our trip response team. So those guys who are in the trip response team, they will have to stop everything else and prioritize the return to service of the trip. Not everyone gets involved. If the trip comes from the turbine area, obviously we will expect that more disturbance will happen on the turbine. Vis-a-vis when the trip comes from the boiler area, we'll get more disturbance from the boiler or any other plant, and then the teams will support.
Is this a 24-hour job dealing with the trip?
It is a 24-hour job, whether we trip during the normal working hours or after hours. So after hours, the shift manager on site will then call the standby teams who will leave their houses back to site to be able to investigate and find the root cause of the trip and determine whether it's safe to return the unit and do it. When we are on site, the teams then respond from site. So it's Monday to Sunday. It's 24/7. We are able to provide that support for that. We never leave a unit because it's after hours.
What's it like having this type of responsibility on your shoulders?
It's a very huge responsibility in a sense that we generate electricity 24/7. So as a general manager, I'm permanently on a call sometimes to assist the teams with certain technical challenges. As you might know, that our country is going through a difficult time. So the availability and we spend much more time on the call, remotely supporting the teams, working extended hours, sometimes also on non-working days. We are always available to be able to make sure that the power station does perform. When we do encounter problems, we provide maximum support from the teams. It's that job where you really are always on duty, whether you are on site or you are at home. And we also have got a couple of remote systems that helps us to be able to see what's going on and support. So I think that is the biggest challenge, that there's minimal time for rest. But the fulfilling part of it is knowing that we are able to help the country where possible. So I think that makes the responsibility bearable, because when we have units running and performing, we can see the direct impact to the energy supply. I think that's what keeps me going, and that's what keeps our teams going, knowing that we have a direct impact on the country, and when we solve our problems, we can see the positive benefits of it.
When you tell people what you do, for example, that you work for Eskom, do you get a lot of negative comments?
Yes, I do get a lot of comments, some negative, some positive, when I tell people that I work for Eskom. I guess the reason being is that as an organization at large, obviously the country is not happy with the state of load shedding and the challenges. And if you work then for Eskom, there is an expectation that you are either part of the problem or part of the solution. But I also get to speak with other people who have an idea of the complexity and the challenges that we are dealing with, and when they see us working extra harder, they have those positive words of encouragement for us to keep going and make sure that the country is well taken care of. But yes, with load shedding, there's quite a lot of negative comments that we receive, that I personally view them as positive criticism that says we still have a lot to do to make sure that we improve the performance of our power station.
I'm sure you frequently interview new candidates for employment. How do you know if an engineer or a technologist is going to be good at their job? What are you looking out for? What are your teams looking out for when they interview new people?
The minimum requirement is you must have the qualification. If we are looking for engineers, we want you to have your BEng, your BSc in engineering or BTech. We are more looking for individuals that are passionate, that will want to make a difference. So we always looking for that energy from the guys who would want to make a difference, because we understand that you can have the minimum qualification that are required, but if your passion is not there, you don't have that right energy. And we understand that there are a lot of challenges in the generation space, and we need then that kind of personalities of people who are driven, who will want to solve the problems and make a difference. So when we interview the guys and we interact, we are looking for those signs that says the attitude is right, the drive is there, and they want to make a difference. The rest, we believe that skill can be taught for them to be more experienced, but attitude is something that someone must bring when they come for an interview, and that passion, we want to see it so that we can then be able to trust that in the midst of challenges, but this person will have a resolve and a drive to make a difference.
What advice do you have for students who are studying to be technicians or technologists or engineers?
My advice to them is that if you are studying engineering or technology, there is a space within South Africa, especially in the power industry, for them to make a huge difference. We need a skill in that area. We need a lot of skill as a country in the area of engineering, so that we can then be able to raise our own specialists that will come up with a lot of innovative ways to resolve our problems. So there will always be space for them to contribute and make a difference in the field of engineering.
You mentioned that we need a lot of skills. Have you faced any challenges with the skills shortage?
Yes, we have faced a number of challenges with skills shortage. Basically in the power plant, where we have activities where we do not have skill, then we will then use the OEMs, the original equipment manufacturers, to supplement our skill in order to resolve those problems. But more importantly, we then contract them to be able to upskill our guys so that in the future we will then have build our own skills. So in the space of the boiler and the turbine, we will have our guys locally, but we will then sign as and when required contracts with those OEMs, so that when we face advanced problems that we have not seen, we can then have our local teams engaging with the guys, whether overseas or already here, so that we can then be able to upskill them.
What are your goals for this power plant?
Our first goal as Kusile Power Station 1 is that this power station needs to be completely, the construction needs to be completed, so that we can then have the biggest power plant that will generate 4,800 megawatts. That's one part. The second part is we are working hard under operations and maintenance to make sure that we optimize the performance and reliability of the power plant, so that it can be able to give the maximum power that it can give in a reliable manner than currently it is. Thirdly, we want to take pride in doing that without harming the environment or harming people around the power station. So those are our three primary goals: to improve the performance, to complete the construction, improve the performance, and making sure that we do that without harm, whether it's people or environment.